All right, let's just jump right in. Got an algorithms exam on the horizon? Then you know directed graphs are a big deal. So today, we're going to build a solid study guide. We'll focus on two really special types of graphs and the key algorithms you absolutely have to know to ace those questions. So let's think about a real-world problem. How do you schedule a ton of tasks when some of them depend on others? I mean, imagine you're building a house, right? You can't put the roof on before the walls are up. And you're definitely not painting those walls until the drywall's installed. That's a classic dependency problem, and it's the perfect setup for the first algorithm we're about to tackle. Okay, so for this explainer, we're really going to zero in on two specific graph structures. First up, we've got directed acyclic graphs, or DAGs for short. The key thing here? No cycles. You can't start at some node, follow a path, and end up back where you started. Think of it like a city with only one-way streets and absolutely no roundabouts. Then we have successor graphs. These are even more specific. Every single node has exactly one way out. Super predictable, right? And because of these unique properties, we can use some seriously efficient algorithms on them. So here's our game plan. First, we'll dive into acyclic graphs, get a handle on sorting and dynamic programming. Then we're going to unlock successor graphs. After that, we'll cover a classic for finding cycles, and then, and this is the important part, we'll pull it all together into an exam strategy guide. Sound good? Let's get to it. Okay, section 1 it is, mastering acyclic graphs. And the first, most fundamental operation, the one that really unlocks everything else, is something called topological sorting. So what in the world is a topological sort? Well, it's actually pretty simple. You're just lining up all the nodes of a DAG in a straight line. The one hard rule is that if there's an arrow pointing from node A to node B, then A has to show up earlier in the line than B. That's it. It's all about respecting the dependencies. The easiest way to think about this is getting dressed in the morning. You can't put your shoes on and then your socks, right? There's an order. The task put on socks has a directed edge to put on shoes. So any valid topological sort of your morning routine is always going to have socks listed before shoes. It's all about that order of operations. So how do we actually find this magical order? We use a good old depth-first search, DFS. We're going to give each node one of three states. You can think of it like a to-do list. State 0 is not started, state 1 is in progress, and state 2 is done. We dive deep down one path of the graph. Once a node has no more neighbors to visit, we say its task is done, we mark it as state 2, and we add it to a list. Now, the most important part, the step everyone forgets. At the very end, you have to reverse that list. You know, this three-state system is also super clever because it gives us a built-in cycle detector. Let's say during our search, we stumble upon a node that's already marked as in progress, that's state 1. What does that mean? It means we've somehow circled back to a task that we haven't even finished yet. And boom, that's a cycle. If you find a cycle, a topological sort is impossible. Game over. Let's quickly trace an example. As our DFS finishes with each node, they get added to our list. Maybe node 6 is a dead end, so it finishes first, then 3, then 2, and so on. We end up with this processed list, 6, 3, 2, 1, 5, 4. But wait, what was step 5? We have to reverse it. And there you have it, 4, 5, 1, 2, 3, 6. A perfect, valid topological order. Awesome. So now that we have this topological order, what can we do with it? Well, it unlocks some really powerful techniques, like applying dynamic programming right on the graph itself. This is part B of our focus on acyclic graphs. A super common exam problem you'll see is something like this. Count all the different paths from a start node to an end node. In a general graph, this can be really tricky, but in a DAG, it becomes surprisingly manageable. Think of it like a project plan. How many different sequences of tasks can get you from the very beginning to the final delivery? The logic here is just beautiful. If you want to know how many ways you can get to some node X, all you have to do is add up the number of ways you could get to all the nodes that point directly to X. It's that simple. And because we process the nodes in topological order, we can guarantee that by the time we get to node X, we've already figured out the values for all the nodes that feed into it. No fuss. And by applying this summing logic all the way through our graph, in topological order, of course, we can find the total number of paths to our end node really efficiently. In the example we've been using, this calculation gives us an answer of exactly 3 distinct paths. Okay, time to switch gears. Let's move on to section 2, unlocking successor graphs. Now remember the rule here. Every single node has exactly one exit. This super rigid structure lets us do some very cool and powerful optimizations. The main property of a successor graph is just pure predictability. From any node, you have no choices to make. The path is set in stone. The structure always boils down to a bunch of paths that eventually lead into one or more cycles. You can almost picture it like a set of rivers all flowing downstream into the same circular lake. All right, here's the classic exam problem for these graphs. Find the node you land on after taking exactly k steps. The simple way is to just, well, walk k steps. That takes O of k time. But what if k is something huge, like a billion? We'd be here all day. We need a faster way. And that's where this amazing technique called binary jumping comes in. It lets us answer that query in logarithmic time. That's O log k, after we do a little bit of pre-processing up front. The method is it's brilliant. Here's how it works. First, for every single node, we pre-calculate where we'd land after 1 step, 2 steps, 4 steps, 8, 16, and so on, all the powers of 2. Then, if we want to make a big jump, say 11 steps, we just break 11 down into its binary parts, which is 8 plus 2 plus 1. So we just make an 8-step jump, then a 2-step jump from there, and then a final 1-step jump. 3 jumps instead of 11. Imagine doing that for a billion steps. It's a massive, massive speed up. Now, whether we're in a big successor graph or just following a single path in any graph, we often need to find out if there's a cycle. This brings us to section 3 and a truly beautiful, classic algorithm, Floyd's cycle finding algorithm, which has the best nickname ever, the tortoise and the hare. Here's the challenge that Floyd's algorithm just completely crushes. You could, keep a list of every single node you visited, but if the path is long, that could use up a ton of memory. Floyd's algorithm is genius because it finds the cycle, its starting point, and its length, using only 2 pointers. That's it. We're talking constant memory, O of 1. It's incredible. Okay, the algorithm works in 3 clear phases. Phase 1, you have a slow pointer, the tortoise, that moves 1 step at a time. And you have a fast pointer, the hare, that moves 2 steps. If there's a cycle, the hare is going to eventually lap the tortoise, and they will meet somewhere inside that cycle. Phase 2, now you need to find the start of the cycle. To do this, you move one of your pointers all the way back to the beginning of the path. Then you move both pointers forward 1 step at a time. The very next place they meet is the exact first node of the cycle. It feels like magic, but it's pure math. And phase 3, finally, to get the cycle's length, you just park one pointer at that start node and walk the other one around the circle until it gets back, counting every step. Easy. All right, let's pull all of this together and bring it home. This is our final section, your exam strategy guide. This is about how to structure your thinking when that exam paper is sitting right in front of you. So this is your core toolkit. Take a look at the time complexities. For DAG problems like topological sort or DP, you're usually looking at OV plus E because, well, you have to look at the whole graph. But for Floyd's, since we're just following one path, the complexity is linear in the number of nodes on that path, OV, but with that unbelievable O1 space advantage. And here are the traps you need to sidestep. I'm telling you, the #1 mistake with topological sort is forgetting to reverse the list at the end. For the DP path counting, it's so easy to miss one of the incoming edges when you're adding things up. With Floyd's, the tricky part is remembering that in phase 2, both pointers slow down and move at the same speed. And maybe the biggest one of all, before you even think about using a DAG algorithm, please ask yourself, have I actually confirmed this graph is acyclic? So, we've gone through the theory, the algorithms, and the strategy. But the real goal here is to start seeing these patterns out in the wild. Think about it. Software build dependencies, course prerequisites at your university, even a complex recipe in a cookbook. They are all DAGs just waiting to be sorted and analyzed. So now that you have the tools, what's the first one you'd tackle?